All right, let's jump into a deep dive on machine learning today. We're going to be looking at auto-encoding variational Bayes. Sounds kind of complicated, right? But actually, it's about how machines learn, and especially when we're dealing with tons of data, even if some of the information's missing.
Yeah, it's like tackling this challenge of hidden variables, like you're trying to bake a cake, but some of the ingredients, they're smudged in the recipe. You can't read them. Those are like hidden variables. They're important, but you can't see them.
Oh, so how would you even figure that out? I mean, you can't just guess, right?
Right, exactly.
Right.
Traditional methods really struggle with this, especially when we have huge data sets. So that's where this idea of variational Bayes comes in. It's a different way to approach the problem.
So like a workaround for those missing ingredients.
Yeah, think of it as you have this tool that can tell you, okay, based on the cake you see and the ingredients you can read, here are the most likely values for what's missing. That's kind of what variational Bayes does. It helps us find the true posterior distribution, which is like a map showing those hidden variables.
So we're not finding the exact missing ingredients, but the most likely ones based on what we do know.
Exactly. And this paper does something really cool. It makes this whole process efficient for computers. They call it reparameterization. It's like finding a shortcut for a really tough equation.
A shortcut. I'm always up for simplifying things. How does that work?
Instead of working directly with those missing ingredients, which can be a lot of computation, they introduce this auxiliary variable, kind of like a stand-in for the missing part. It makes the calculations much faster.
So we're basically replacing a complex equation with a simpler one that still gives us a good result.
You got it. And that's the core idea behind their auto-encoding VB algorithm, AEVB for short.
Okay, so AEVB uses that trick to learn. How does that actually happen?
It's kind of like a two-step process. You've got an encoder and a decoder, like when you compress and decompress a file.
So the encoder's figuring out the missing ingredients, right?
Exactly. It takes the data we do have and tries to approximate those hidden variables, like a detective looking for clues. Then the decoder comes in and tries to rebuild the original data using those guesses from the encoder.
So how do we know if it's working? Do we compare the reconstructed data with the original?
Exactly. The algorithm is constantly checking how well it did and adjusting to minimize the difference. That's where those SGVB estimators come in.
Right, those estimators, what are they doing?
They're like quality control checkpoints, making sure the learning process is on track. One estimator compares things to what we already know. Like, do these guessed ingredients make sense for a cake? The other estimator checks how well we rebuilt the data. Is the reconstructed cake close to the real one?
This is all sounding kind of familiar, like the idea of autoencoders.
You're right, there's a connection. Both autoencoders and this AEVB algorithm, they're trying to efficiently compress and reconstruct data. But the variational approach, the one this paper uses, it has a special advantage. It avoids something called arbitrary regularization techniques. Those are common in autoencoders, but sometimes they lead to less accurate results.
So it's like a more precise way to bake that cake.
Exactly. The variational approach is more principled. It guides the learning process better.
So we've been talking cakes, but did they actually test this on real data?
Yes, they did. They used a couple of image data sets. One was MNOST, which is handwritten digits, and the other was Frey faces, a data set of faces. And the AVB did really well. It actually outperformed other methods.
So this isn't just theory, it works.
Yeah, and what's really cool is they use this method to visualize complex data, so we can actually see the hidden structures.
Wow, that's amazing. How did they do that?
They created 2D manifolds. Think of them like maps showing how data points relate. One for MNOST and one for Frey faces.
So we can see how different digits or faces are grouped together.
Exactly, based on their similarities.
That's incredible. But before we go too far, can we unpack some of these technical terms? Like, what does intractable mean in this context?
Right, sometimes the language can be a bit confusing. Intractable basically means the calculations become way too difficult for computers, even with all their power.
So like hitting a wall, how do they deal with that in this paper?
Yeah, it's like they hit a wall. And that's where the variational approach is so smart. Instead of trying to break through that wall, it finds a way around. By focusing on what we call a lower bound. Imagine you're trying to measure Mount Everest. Getting the exact height is tough, right? But you could find the height of base camp, which is definitely lower than the summit. That would be your lower bound, a guaranteed minimum.
So it's like finding a good enough solution that's still accurate but easier to calculate.
Exactly. And that's how the AEVB algorithm handles those intractable problems. It's a compromise, but a smart one.
Makes sense. Did they compare AEVB to other algorithms? Like, how does it stack up against the competition?
Oh, yeah, they did. They compared it to something called wake sleep, another way to deal with those hidden variables. And AEVB consistently did better, both in speed and accuracy.
Wow, that's impressive. But I also remember them mentioning Monte Carlo EM. How does AEVB compare to that one?
Monte Carlo EM, or MCEM, that's a more traditional method. It uses a technique called Markov chain Monte Carlo to sample from that posterior distribution, the map we talked about. But MCEM can be really slow, especially with big data sets.
So it's like taking the scenic route. It takes longer.
Yeah, exactly. And the results showed that AEVB was way faster than MCM, especially on large data sets. In fact, MCM was basically unusable for the full MS data set. It just took too long.
That really shows how efficient AEVB is. It seems like this research is pushing the boundaries of how machines learn and understand data.
It is. And even though the technical details are complex, the takeaway is that this AUVB algorithm, with that reparameterization trick, it's a big deal for machine learning. It's opening up new possibilities in image recognition, language processing, data analysis.
You mentioned earlier that they use it for visualization too. Can you tell us more about that? Seeing hidden structures in data sounds super powerful.
Absolutely. Remember those 2D manifolds, the ones for MNIST and for A-faces. Those are the visualizations.
So what did they actually see? Can you give some examples?
For MNIST, imagine a map where each point is a handwritten digit. What they found was similar digits were clustered together, all the ones in one area, the twos in another. It shows that the model learned the structure of the digits. Certain shapes are more likely to be certain numbers.
So it's not just randomly labeling images, it's actually understanding the shapes.
Yeah.
What about the free faces?
Similar thing. Each point on the map was a face. Images with similar features were grouped, same expressions, same head poses, like the model learned a face space, different regions for different characteristics.
So it organized faces by how they look, just like we do.
Exactly. And this visualization has so much potential in different fields. Imagine seeing patterns in medical data to diagnose diseases, or understanding financial markets for better investments.
Yeah. It's like having a new way to see the world. But this all seems very focused on images. Could this method be used for other types of data too?
Yeah, definitely. This paper focused on images, but the ideas can be applied to other data too. It's all about learning, even with hidden information. So if you can represent your data the right way, you could use this for financial stuff, text, even sensor readings.
That's amazing. So many possibilities. Predicting the stock market, understanding climate data, but could we even use this to understand human behavior? So much of what drives us is hidden. Our motivations, our beliefs.
That's a really interesting question. Human behavior is complex, for sure, lots of hidden factors. But with this approach, we might be able to approximate those variables, like figuring out the secret recipe that makes us tick.
Imagine creating a map of human behavior, seeing clusters of people with similar motivations.
Yeah, he could revolutionize psychology, marketing, even politics, understanding why we do what we do.
But we have to be careful too, right? Ethical considerations with such powerful tools.
Absolutely. It's important to use this responsibly, not for manipulation or exploitation.
But the potential benefits are huge, helping people with mental health, personalized education.
Exactly, using this knowledge for good.
This deep dive has been fascinating. So many ideas from just one paper.
It really shows how fast machine learning is moving.
And how it's impacting everything.
It's a really exciting time to be working in this field.
If you're interested in learning more and want to understand variational Bayes, check out the paper, Encoding Variational Bayes.
It's a challenging read, but worth it.
And remember, even if the technical stuff seems tough, the main ideas are actually pretty intuitive.
Yeah, finding ways to simplify complex problems, uncovering patterns, understanding the world better.
Maybe these algorithms will even teach us about ourselves. Something to think about.
Absolutely, the journey of discovery never ends.